Hi, this is a video to help you through the activity on hydrocarbons fatty acids and alkane nomenclature. In the screen in front of me, I have a table of functional groups. I'd like you to notice that the functional groups are organized into families, and families are organized into categories. The functional group is what is used to categorize these things into families. So the family and the functional group are technically different, and the molecules are always going to be grouped into families according to their functional group. This is addressed in number 6 on your activity in front of you. The difference between a family and its functional group is that a functional group is used to categorize a molecule into families. The functional groups are important to know about because they tell you the reactivity that a molecule will have. They literally tell you the function as far as the chemical reactivity of the molecule. So if you know the functional group and if you know the family that the molecules fit into, you know something about their reactivity. Please notice that alkanes do not have functional groups. Alkanes are not reactive, and so they do not have a function or a functional group. So anything that doesn't have a functional group is going to be categorized as an alkane. Most of these families or categories on this slide are very interesting as far as their chemistry goes, but the chemical reactivity comes from the polarity of their bonds. Today, we're going to focus only on the hydrocarbons. These things are very nonpolar, and so they're not very reactive. Polarity is what gives a molecule its reactivity, and the hydrocarbons are not very polar, so they are not very reactive. On the paper in front of you, you should have a table that looks like this. Notice that these skeletal structures do not contain any heteroatoms, or in other words, they don't contain any atoms that aren't carbon or hydrogen. These molecules have in common that they are hydrocarbons. They are molecules that are made only of carbon and hydrogen atoms. Because carbon-carbon bonds and carbon-hydrogen bonds are nonpolar bonds, all of these molecules are nonpolar. So they're not very reactive if we remember that reactivity is related to the polarity of a molecule. What I'd like to focus on now is categorizing each of these hydrocarbons into its appropriate family. The first molecule only has carbon single bonds, and therefore it's an alkane. It doesn't have any functional groups. Molecule number 2 on your activity has most of the carbon-carbon bonds as single bonds, but it also contains one carbon-carbon double bond. This makes it an alkene, and it fits into this family of molecules that has the functional group of a carbon-carbon double bond. Molecule number 3 has one carbon-carbon triple bond, and therefore it fits into the family we call alkynes. Molecule number 4 here is a little tricky. Even though it has carbon-carbon double bonds, this molecule fits into a higher order group called the aromatic group. Anytime you have a ring that has alternating double and single bonds, just as this molecule does, it is an aromatic functional group. This is different from the molecule over here, which does not have single double bonds that are alternating around the ring. So here we have an alkyne. Again, we have an alkene. 2 of them now this time, but this whole molecule fits into the alkene family. And because this is simply an alkane, it fits into the alkene family. There are no functional groups on this molecule. Remember, to be an aromatic compound, you must have alternating single and double bonds, and this molecule only has single bonds. Now I'd like you to turn the page and look at the table that's given. I'd like you to notice a few things about the information in this table. First of all, please notice that all of the names of these alkanes end in the same suffix, the ane suffix. This ending comes from the fact that they are in the alkane family. In fact, every alkane has a name that ends in ane. I'd also like you to pay particular attention to the prefix on these names. The first part of these names is meaningful. Meth means that there's one carbon. eth means 2 carbons, prop means 3 carbons, and but means 4 carbons, and then so on and so on. After 5, these are pretty familiar to you, but 1 to 4 are probably new. Notice that these names are important for understanding how many carbons are in the molecule, and please remember these and be familiar with these for later on in today's activity. We'll see them again soon. 2 other things to notice. First, notice that this table is organized from the smallest molecules on the top to the largest molecules on the bottom. As the number of carbons increases from top to bottom, the size of the molecule also increases. And please also notice the trend in the boiling points. The boiling points are increasing with size. This is an important trend that we will talk about again later on in the semester. For now, just notice that it's happening. I also would like you to notice that there is a trend or a pattern in the molecular formulas. Each time that the molecule gets bigger, when you add 1 carbon, you add 2 more hydrogens. This is a very useful pattern to know. If you know the generic molecular formula for an alkane, you'll be able to draw isomers easily. Let me talk about this a little bit more. Sometimes it's easier to see in pictures. So I've drawn the Lewis structures of the first 5 alkanes in your table. Here is methane, ethane, propane, butane, and pentane. Notice that each time I add a carbon, I also add 2 more hydrogens. In fact, for each carbon in this molecule, you can see that there are 2 hydrogens attached. And then at the ends, there's an additional hydrogen at each of those ends. So we can come up with a generic molecular formula for an alkane of CnH2n plus 2. So for the number of carbons that you have twice as many hydrogens, right? Plus 2 more, 1 for each end. This is the case for linear alkanes. Linear alkanes are just any alkane that doesn't have a ring. So if you can get used to knowing that this type of formula means that you have a linear alkane, it's easy to recognize the molecular formula of an alkane as opposed to something else. This is different than you would see for a cyclic alkane. For cyclic alkanes, you would essentially have to remove 2 hydrogens to bring the ends together and make a bond between the 2 end carbons. Therefore, the general formula of a cyclic alkane is CnH2n. Here's a picture. So if I took away these 2 hydrogens on this molecule and I connected the 2 carbons at the end, I would have a cyclic alkane. Anytime you need to make a ring in a molecule, you essentially lose 2 hydrogens from the linear alkane formula. So this is the generic formula for a cyclic alkane. This is also the same type of formula you'll see for alkenes. Anytime you need to make a double bond, you'll lose 2 hydrogens from the linear alkane formula, because if you needed to make a double bond between these 2 carbons, you would have to take away 2 of the hydrogens. So cyclic alkanes and alkenes have this type of formula. Anytime you make a ring or a double bond, you have to take away 2 hydrogens from this generic linear alkane formula. When a molecule is full of hydrogens, or when it has as many hydrogens as is possible, it is said to be saturated. The molecules over here that are linear alkanes are saturated. When a molecule does not have as many hydrogens as possible, it is called unsaturated. So this molecule here, where it has a double bond, it could technically have 2 more hydrogens. And so this is an unsaturated molecule. We'll talk a little bit more about saturated and unsaturated in just 1 minute. For now, I want to focus on the formulas. It's useful to be able to recognize these types of formulas because if you're given a formula, then you can recognize what you're dealing with. Let's say I ask you to draw isomers of C5H10. The first thing that you would want to do is look at the formula and decide what you're dealing with. So notice here that C5H10 has twice as many hydrogens as it does carbon. And that means that it fits into this category. It's either a cyclic alkane or an alkene. And so when you would draw the isomers for this formula, you would have to make sure that each isomer had a ring or a double bond. And you could recognize this from the formula more quickly than you could if you would have to draw out the Lewis structure and figure out what was missing. Likewise, if I gave you the formula C5H12, like I did in number 4, you would know that you're just drawing regular alkanes, so no rings and no double bonds. So C5H12 is a linear alkane, and there are several isomers of this. Whenever you're asked to draw all of the possible isomers for a formula, just like you are in number 4, you want to do this systematically. So let me give you a hint as to how you should go about doing something like this. When you're given a formula like this, the first thing you want to do is draw out the longest chain. If my molecule has 5 carbons in it, then I would start with 5 carbons in a row. And I would draw that isomer. That's the only isomer possible for the longest chain, is basically all of them all in a row. And then what you want to do is make the chain shorter and shorter and draw as many isomers as possible in each case. So the next thing I would do is draw out a 4-carbon chain, and I would add the 5th carbon as a branch. Whenever you do something like this, always start at the 2nd carbon, because if you start at the 1st carbon and add the branch there, you've just made a new 5-carbon piece, which is the same as the first thing that I drew here. So always draw the branch on the 2nd carbon for a situation like this. And then this is the only isomer I can draw with a 4-carbon chain. And so therefore I'd move down again and try to do the 3-carbon chain. And so in this case, if I draw a 3-carbon chain, I have to draw 2 different carbon branches off the middle carbon so that I have 5 carbons and that it fits this formula. These are the only 3 isomers of C5H12. Anytime you're asked to draw isomers, I recommend starting at the longest chain and then shortening your chain by 1 carbon and drawing as many isomers as possible. This will help you to complete the problem systematically and will avoid missing any of the possible isomers. In a moment, we're going to talk about how to name things like this. But first, I want to talk about fatty acids. So hydrocarbons are really useful in biological systems, but they're normally parts of larger or more complicated molecules. Hydrocarbons show up in fatty acids. We'll talk more about fatty acids later in the semester. For now, I just want to talk about some basic characteristics, and I want to talk about how you name these things. Fatty acids are amphipathic. They have nonpolar and polar parts. The nonpolar part is the hydrocarbon tail, and there are some things that you should know about these. The hydrocarbon tail, in biologically relevant fatty acids, those that are made in our bodies or by other animals or plants, are usually a total of 12 to 22 carbons long with even numbers of carbons. They can be saturated or unsaturated. Remember, saturated means that it has the maximum number of hydrogens possible. When you only have single bonds in that fatty acid tail, it is saturated. And when you have a double bond or any double bonds, it's an unsaturated fatty acid. These are the saturated and unsaturated fats that you hear about in nutrition. Anytime you do have an alkene in your fatty acid, it should be cis, unless you're told otherwise, because natural fatty acids are always cis. Fatty acids also have a carboxylic acid head group, and this is a polar part of the molecule. The last carbon in the chain has a double bond to an oxygen and a single bond to a hydroxyl group. This is a carboxylic acid functional group, and this is one of the most important functional groups in biological systems. You will get very, very familiar with carboxylic acid functional groups this semester. The name fatty acid comes from the fact that there's this non-polar region, which is fatty, and an acidic or acid head group. So this is literally a fatty acid. The word amphipathic refers to the fact that it has both kinds of characteristics. It's nonpolar and polar in the same molecule. They kind of have a double personality. We'll talk about it later when we talk about the properties of these molecules. For now, I just want you to understand that they have nonpolar and polar parts, and I'd like you to know how to name them. We're going to learn the systematic naming for fatty acids, and this is the numeric system. There are also common names for all of the fatty acids, but I'm not asking you to memorize them. Understand how the systematic naming works, and you'll be able to draw any fatty acid. On your activity, I've labeled the first and last carbons on both of these fatty acids. Here, I'll number them for you. So this is carbon number 1, and this is carbon number 18. 1 and 18. Both of these molecules have 18 carbons on them. Notice that the first number in brackets in the naming system means the number of total carbons in the molecule. The second number in the brackets tells you the number of double bonds or unsaturations that are in the molecule. Notice that this one has 0 unsaturations, and so the second number is 0. And this one has 1 unsaturation, so the second number is 1. The first and second number are written in brackets and separated with a colon. When you have a double bond, you have to know where the double bonds are. The double bond will start on the omega number. Notice that this one's 18,1 omega 9. The 9 stands for the number where the double bond starts. And it's assumed that the double bond is between that number and the next highest number. Always start numbering these fatty acids at the carbon farthest away from the carboxylic acid. There are some examples in your activity which I'd like you to try. Make sure you check your work and know that anytime you see the name of a molecule, you'll always know the number of carbons, the number of double bonds, and where the double bonds start. If you have more than one double bond, the second double bond will always start 3 positions away from the first. So in this example, if I started my first one on 9, let's say I had 2, then the first one starts on 9, then the next one would start 3 carbons later, which would be on 12. So there are some examples for you in numbers 4, 5, and 6. Make sure you check the key so that you know that you are correct and that you understand how to draw structures from the numbers. Please make sure you're using skeletal structures, that you're drawing your double bonds in the cis orientation, and that you're adding your carboxylic acid to the correct carbon. If you have any questions, please ask a friend or make office hours appointments. Now I'd like to switch gears and talk about naming alkanes. An alkane name can be broken up into 3 parts. The first part tells you what substituents and where they are. The second part tells you about the longest continuous chain of carbons. And the last part gives you the family suffix. Since we're learning to name alkanes right now, all of your family suffixes will be ane for alkane. There are detailed instructions on your activity and in your textbook. I'm briefly going to go over some of them right now, but not all of them. The easiest way to learn how to name alkanes is to just start naming them. But first, I'll very briefly go over the rules. First thing is to identify the longest continuous chain of carbon atoms. This is the parent chain. Then you want to identify the substituents coming off the parent chain, and you want to name them. Alkyl substituents have an -eel ending instead of ane. There's a table in your activity that lists a few of the important substituents that you will see. Remember earlier in this activity, I told you to remember those prefixes or the first parts of the names of the alkenes? Here they are again. Meth, eth, prop, and again prop. Methyl is just a substituent that has 1 carbon. Ethyl is a substituent that has 2 carbons, and propyl is a substituent that has 3 carbons. Isopropyl is just a different type of 3-carbon piece, which is connected at the middle carbon instead of the end carbon. If you have halogen substituents, you end them in O instead of the ine. For example, if you had a fluorine, you would call it a fluoro substituent. After you've identified the substituents, then you number the parent chain so that the first substituent is on the lowest number And if there's any tie, you use alphabetical order to decide. Write the name after you've done all of these things. There are a few more details in your activity, and make sure you read them after we do a few examples. Here's an example. Let's follow the steps. First, identify the longest chain. The longest chain is 4 carbons. Then identify the substituent. This substituent is a methyl group. The next thing I want to do is number the main chain so that the substituent is on the lowest number carbon. In other words, start numbering at the end of the chain closest to the substituent. 1, 2, 3, 4. Okay. And then the next thing to do is just name the molecule. Substituents, or the first part of the name tells you what and where. The methyl group is on the second carbon, so you will call this 2-methyl. The main chain is 4 carbons long, and so you put the part that means 4 carbons, which is bute. And since this is an alkane, you end it in the family suffix ane. This is one word. The number that corresponds to the substituent is separated from the name with a dash, but there are no spaces. So this would be called 2-methylbutane. This is the same molecule. And if you can't see that, naming it would help. First, identify the main chain, identify the substituent, number the chain starting at the end closest to the substituent, and then name it. This is 2-methylbutane. Even if 2 molecules are drawn differently, you'll know that they are the same thing if you name them properly and they have the same name. Let's try some more examples. Here's an example that's written out in a condensed structural formula. The main chain here is 7 carbons long, and I can see the substituent is here in parentheses, and it's only 1 carbon, so it's a methyl group. It doesn't matter in this case where I start numbering, because the methyl group is attached to this carbon, and this carbon is directly in the middle of the chain. So I could start from the left or the right. Either way, I end up with this carbon being number 4. This molecule is 4-methylheptane. Hept means 7 carbons, and the 4-methyl tells you what and where the substituents are. ane tells you that it's an alkane. Here's an example where you have 2 substituents that are the same. Again, the longest chain is 7 carbons long, and there are 2 different substituents. Both of them are methyl. When you have 2 of the same substituents, you just write that in the name by calling this a dimethyl. So you use a little bit of a prefix. So here I would call this a dimethylheptane. And I would say where the substituents were using these numbers. So this would be 2,5-dimethylheptane. In the next example, I have, again, a long chain that's just written in a line. And now I have an isopropyl substituent. Number the chain. In this case, once again, it doesn't matter where you start numbering. You could start from the left or the right. You'd still end up with this number, or this carbon as number 4. And this is 4-isopropyl-heptane. In the next example, you have a methyl and an ethyl substituent. Number the main chain starting at the end closest to the first substituent. And now, pay attention. This methyl group is on the second carbon, and the ethyl group is on the 5th carbon. When you write the name, you always put these substituents in alphabetical order. This would be called 5-ethyl-2-methyl-octane. The 5 is separated from its substituent by a dash. And then you separate 2 different substituents with another dash. Then the number, and then the dash and methyl. Oct for the number of total carbons, and ane because it's an alkane. Naming cyclic alkanes is similar, except you have to use the prefix cyclo in front of the parent chain name. When you're naming cyclic alkanes, the ring always serves as the parent chain and starts with cyclo. Then you identify the substituents, number the ring, and assign the number so the most substituents are on the lowest number. Again, the alphabet can help you decide where to start. If there are two substituents, you have to determine whether they are cis or trans to each other. We're going to talk more about cis and trans in the next activity. But here's some examples. Basically, the ring has two sides. If both of the substituents are on the top of the ring, they're written as these wedge lines. So they're coming out at you. They're closer to you. If both of the substituents are on the bottom of the ring or they're facing away from you, they are shown in dashed lines. When you have two substituents and they're both on the same side of the ring, it's called a cis isomer. On the other hand, if one is up and one is down, they are across from each other and they're called a trans isomer. After you've identified whether it's cis or trans, you write the name indicating cis or trans, and don't forget to use your cyclo prefix on the parent chain. Let's look at some examples. Here we have a ring that has 4 carbons. 4 is represented with bute, and so this is simply cyclobutane. Here we have one that has 5 carbons in a ring, so the main chain is cyclopentane. And here we have 1, 2, 3, 4, 5, 6, 7 carbons in the chain, and so this is cycloheptane. When you have a substituent, you just simply identify it and treat the ring as the parent chain. So here you can number the ring. When you have only one substituent, it's not critical. But you can call this 1-methylcyclopentane, or you could just drop the 1 because this is an unambiguous name. There's no other way that you can draw methylcyclopentane that is a different molecule than the one that's drawn. Likewise, in this molecule here, this is a cyclohexane with a bromo substituent. I could call this 1-bromocyclohexane or bromocyclohexane. When you have 2 substituents, you cannot drop the numbers, and you have to indicate whether they're cis or trans if they're drawn with the wedge and the dashes. So in this case, I have 2 substituents. I have a chloro and a methyl on my cyclopentane chain. Now, where do I want to start numbering? Well, I want to start at the substituent that comes first in the alphabet. So I would start at chloro, and then I would want to go counterclockwise because otherwise I would put my methyl group on a higher number than I would need to. So I would number like this so that chloro is 1 and methyl is 3. And then I list them in the name in alphabetical order as well. Don't forget that these are trans. So this is trans dash 1 dash chloro dash 3 dash methyl cyclopentane. All one word, no spaces. Let's do 2 more examples just to make sure you've got it. In this example, I can see my main chain is written straight across. I have a methyl substituent, an ethyl substituent, and a bromo substituent. So now, in this case, I really have to pay attention to where I'm numbering. If I start over here, my first substituent would be on number 2. And if I start over here, my first substituent would be on number 2. But then where would my second substituent be? Here it would be on number 4, and if I started over here, it would be on number 6. And so I'm going to start at this carbon. And then I list the substituents in the name in alphabetical order. The name would be 2-bromo, 4-ethyl, 8-methyl nonane. In this next example, notice that the longest continuous chain of carbons is not written straight across the page. This is very typical. Here, I basically put my pencil on one end and I try to trace as far as I can go without lifting my pencil. If I start here, I could go this way, but that's only 1, 2, 3, 4, 5, 6 carbons. If I start here, 1, 2, 3, 4, 5, and go down 6, 7, this is actually my longest chain, and that is the parent chain of the molecule. The parent chain is the longest continuous chain, not always the chain that's just written straight across the page. So now I want to circle my substituents. My substituent is a chloro and a methyl group. I'll number so that my substituents are on the lowest number, and since there's a tie here, my alphabetical order wins. And then I just name it in alphabetical order. 3-chloro-5-methylheptane. This is the end of the video. Please make sure you complete the check for understanding for the hydrocarbons and fatty acids section and for the alkane nomenclature. There are some more specific rules in your activity and in your textbook than what I covered here. Please read carefully through them now that we've had some practice. Thanks for watching this video on hydrocarbons, fatty acids, and alkane nomenclature. If you have any questions, feel free to post them in the comment section, and please don't forget to vote if you like this video.